Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this work 2 for the chemical bonding work, which you will have been assigned in your in your assignments for your homework or for your classwork. So we have this table that shows information about diamond and carbon dioxide. So both of them are your case studies in your Cambridge International syllabus, as well as any 14 to 16 years old curriculum all around the world. So we know that this is an allotrope of carbon. Allotrope meaning different forms of the same element. So carbon can be diamond, can be graphite, so they are just different forms of carbon. So this is a giant covalent structure or giant molecular structure, but this is a simple molecular structure, and as such it exists as solid at room temperature and pressure. In fact, it has got a very high melting and boiling point. This exists as a gas at room temperature and pressure, room temperature being 25 degrees Celsius. So if it is a gas at room temperature at 25 degrees Celsius, it already boils by the time it reaches room temperature. So in fact, it has low melting and boiling point. So the structure of diamond and carbon dioxide are different, but the bonds are similar because each of these is a covalent bond. And then between the molecules, you have intermolecular forces. It's the same intermolecular forces that exist between layers of graphite, is what you call van der Waals forces. Whereas this one is all covalent bond. It's a giant three-dimensional network where each carbon is bonded to 4 other carbon, meaning to say the carbon is completely uses all the valence electron for bonding, right? So it's a three-dimensional network with a lot of these strong covalent bonds within the network. So write down the similarities, some similarities between the bonds in diamond and also carbon dioxide. So it said the bonds, and it said in diamond and also carbon dioxide. What can I say? Each carbon in diamond and graphite, not graphite, and carbon dioxide forms 4 covalent bond. Okay, what else can I say? The bonds in diamond and also carbon dioxide. The bonds in diamond and carbon dioxide. Maybe I write another point. What else can I say? So here the carbon is bonded to carbon because it's an element. It only consists of one type of atoms. This is a compound. It has a carbon bonded to 2 oxygen. So there are 2 elements that are combined in a fixed ratio, chemically combined in a fixed ratio. So this is a compound. I don't know, what else can I say? However, each carbon is bonded to 4 other carbon atoms. In diamond, for CO2, each carbon is bonded to 2 other oxygen atoms. 2 times double bond. I don't know what else are the same actually. The bonds are similar. I can't really talk about the intermolecular force because the intermolecular force are clearly different. The bonds, they don't say the covalent bond, they just say the bond. I can probably describe. So I think what I've just done here is this is not similarity, this is differences. Okay, so this is difference. I can probably talk about the sharing of electrons instead. Okay, for this covalent bond, the central carbon atoms share all its 4 valence electrons for forming covalent bond. Four times single bonds for diamond, and then 2 times double bond for CO2. So in hindsight, I really shouldn't be talking about differences, because this is a difference and they want similarity, so I wasn't really addressing the question that well, okay, because I really wasn't sure what they were asking, to be honest. Okay, so next bit is why diamond is a solid, why carbon dioxide is a gas. So this is the kind of question where you will have done in your checkpoint, where it's about the difference in states of matter, and the difference in states of matter come down to melting point and also boiling point. So this is a solid. In fact, it has high melting point and boiling point. This is a gas. It has low melting point and boiling point. So this question could alternatively be asked why diamond has a high melting point and boiling point, why carbon dioxide has a low melting point and boiling point, but instead they choose to ask it in terms of the difference as a states of matter. So this is down to structure and bonding. So they're very generously provided you the structure above, but you should know the giant covalent structure or giant molecular structure. So the giant is essential to distinguish it from simple molecular structure. Therefore, melting, because I'm talking about solid, so I need to think about melting before boiling. So melting diamond requires breaking. So these are like a fixed assay, right? Breaking many strong covalent bonds. And we just want to contextualize the assay in the context of this question. So this is between carbon atoms. Okay, so I'll compare the amount of energy required to do this versus the amount of energy to break whatever we need to break for carbon dioxide, depending on the structure, as a final point, because this is a comparison. Okay, so if I compare now and I compare later, it's kind of repeating the same thing, so I don't want to repeat them twice, so I just compare them at the end, but I'll remember to compare. All right, so CO2, carbon dioxide, has a simple molecular structure. A simple molecular structure, so it always comes down to structure and bonding, even when question doesn't instruct you. Therefore, I talk about boiling because it's talking about gas. Gas is from liquid to gas, so you know, boiling CO2 requires breaking only weak intermolecular forces. You see how we used strong previously, now we use weak, and we specify exactly what we are breaking. Okay, intermolecular forces between the discrete single molecules of simple covalent structure. Overall, we need much more energy, or much more energy is required to break covalent bonds. In fact, the many covalent bonds within the three-dimensional giant covalent structure. Then breaking weak intermolecular forces. So this last point is really to qualify why one has a high melting point and why one has the low boiling point. Therefore, high melting point for diamond and low boiling point for CO2. Okay, so this last one is probably not really required because I already compared the energy, and this is just restating the question, which is probably not essential at all. Question 2. So methane is a major constituent of natural gas. So draw a dot and cross. They specify already. Hydrogen as dot, carbon as cross. They want only the outer shell electrons, so meaning to say that it's just valence electrons, so there's no need to draw the inner shell at all. So carbon, if I draw the display formula for methane, this is display From the display formula, you can count carbon from 4 bonds because carbon is in group 4, 4 outer shell electrons, 1, 2, 3, 4. Hydrogen only has 1 outer shell electrons, it forms 1 covalent bond, 1, 1, 1, 1. So this is the correct structure for CH4. Each of these lines is a single bond, that means 2 electrons being shared, one from this, one from this. So I have cross dot hydrogen, cross dot hydrogen, cross dot hydrogen, cross dot hydrogen. In all my dot and cross, I always like to draw without the shell itself, but it's really up to personal preference. If you like to draw the shell, you like to draw the shell. I don't like to draw the shells, therefore I do not draw the shell. Okay, both would have been equally acceptable because the shell is not a real physical shell. You gotta appreciate that the shell is not a real physical shell. It's simply the region of space where the electrons are most likely to be found. And here, these are localized bonding electrons. They are fixated there because they are attracted towards the positive charge in the 2 nuclei, which contain protons and therefore are positively charged, and they're attracted towards these localized bonding electrons. And guess what? That electrostatic force attraction is the very definition of covalent bond as stated in the syllabus as well as your notes. Okay. Next one, at a temperature of -5 degrees Celsius and a pressure of 26 atmosphere. 26 atmosphere is quite high, so the pressure that we are living at the moment on sea level, if you are not living like on Mount Everest or wherever, is about 1 atmosphere. So 1 atmosphere is like standard atmospheric pressure. -5 degrees Celsius is much below our room temperature. This is much higher than the atmospheric pressure. Methane combines with water and forms an ice-like structure. So methane is a gas at 25 degrees Celsius and atmospheric pressure, but it forms an ice-like structure called methane hydrate. As usual, you know, hydrate, hydro, aqueous, they all refer to something with water. Large quantities of methane hydrate have been found underground. So it's not surprising that as you go deeper underground, just like submarine going below sea level, your pressure gets higher and higher and higher. So 26 atmosphere is most likely to be found underground. Describe the arrangement and motion. So I decided to label this 1 and 2 because I'm very forgetful and sometimes I forget to do things when I don't label them, when I don't circle, when I don't underline, when I don't read question. For 2 marks, I should really talk about the 2 things. This is really talking about solid. This is your states of matter, where they say in the syllabus you should know separation, energy, what else, motion, as well as arrangement, right? In all those things back in topic 1 under states of matter. So the solid particles or the solid molecules or whatever, particles, molecules. So the solid particles are closely, nope, not just closely. In fact, solid are not closely. Solids are tightly packed. Okay, and then the motion. Solid particles can only vibrate about their fixed position. Can only vibrate. This is motion. How are they moving? About their fixed position. So the methane hydrate underground has not yet been extracted in large amounts because when you extract it, large amount of methane are released. So the methane hydrate is what you found underground at high pressure and low temperature, but when you extract it, large amount of methane are released. You want methane hydrate, but when you obtain it, when you extract it, all you release is methane. So what happened to the hydrate, the water bit? Therefore, suggests 2 reasons why it decomposes when you extract it. When we extract it from underground, we are bringing it to our level ground. Okay, so we are bringing it up onto our level ground. Our level ground is not going to have this temperature. Look at this. This one, at the temperature of this, at this pressure, these are underground. So when you bring it up to ground, when you extract it, the temperature is no longer this, which is probably why any of the ice-like structure, the water, the ice will have melted, and therefore there's no more water when you take it out, it's just methane. Okay, And of course, our atmospheric pressure is not going to be 26 atmospheres because that is found underground. So when you take it out, again, that is not the environment at which this methane hydrate actually formed underground. So when extracted, we bring the methane hydrate to our ground level. Or environment, where 1, temperature is way above or higher than that. Excuse me. Therefore, any ice would melt. And then number 2, pressure is not 26 atmospheric pressure, meaning very high pressure. Therefore, the condition at which it initially formed under are not satisfied when we take it out, when we extract it. Okay, but the idea really goes back to what are the conditions at which it exists in, and when we extract it, we're bringing it to our ground level and no longer underground, where of course these two are no longer the same. It's a suggest question, it's a little bit of thinking, as well as it requires a little bit of reading through the questions, and that is how O-level questions are like, and that is how the A-level question will be like when you move on to A-levels, and therefore you will not be moving to A-levels until you can master how to address O-level question very well. Question 3. Carbon and graphite are two forms of carbon. So there's a proper name for this. This is called allotropes. Allotropes are the different forms of the same element, such as graphite and diamond. Graphite is used to make lubricants for engines. Explain in terms of its structure why graphite can act as a lubricant. So graphite has this layered structure, layered hexagon, where each carbon is bonded to 3 other carbon, and you have these weak intermolecular forces that you call van der Waal. So this is the person's name who discovered and coined this term, force attraction, van der Waal forces between the layers. And because of the layered structure, you can slide each layer over another layer easily, and therefore they're useful as a lubricant because of its sliding of the layer over each other. So the layered structure of graphite has weak intermolecular force, which you can define as, which you can name as van der Waal forces between the layer. Between the layers, I already say it's weak, so these are easily overcome. These are easily overcome by sliding one layer over the other, layer. Therefore, can be a lubricant, or therefore has lubricating properties. Okay, so you need to talk about the layer structure and the weak intermolecular forces. You also need to talk about overcoming these van der Waal forces when you slide one layer of the other. That's the whole point of this layered structure. Now describe, so a lot of words, differences, two differences between diamond and graphite structure. Okay, so I cannot say giant molecular structure because both of these are giant covalent structure or giant molecular structure. So what is very obvious straight away is the carbon here is bonded to 4 different carbon. If I choose one central carbon here, so you'll see it's bonded to 1, 2, 3, and 4. So I can use another ink. 1, 2, 3, and 4. Each carbon in diamond is bonded to 4 other carbon, whereas each carbon in graphite is only bonded to 3 other carbon. Okay, so that can be my first structure. Of course, the second thing is that there's no layered structure in diamond, whereas graphite is layered with weak intermolecular force in between that are easily overcome, allowing to have lubricating properties. And then here, you don't have this layered structure. In fact, you have a rigid RIGID, a very rigid structure, which is in 3 dimension, because each carbon is bonded to 4 other carbon. So there's no intermolecular forces or whatnot. And this is 3-dimensional network with a lot of strong covalent bonds. Therefore, diamond is very hard, whereas graphite is very soft and is used as a lubricant. But they don't ask us to explain the difference. They just ask us to describe the difference. Okay. So diamond has a 3-dimensional network of strong covalent bond in a rigid framework, therefore very hard. Do I really want to say very hard? Because I just saw the next question. The next question is talking about why graphite is soft and diamond is hard. So it feels like I'm really explaining that. So perhaps I can save the very hard for later on. I just say it has a rigid framework. Whereas graphite has a layered structure with weak van der Waals forces between the layer. Van der Waals forces between the layer. Okay, talking about the second difference now. I can talk about the number of bonds formed for each carbon. So each carbon in diamond forms 4 covalent bond to 4 other carbon, to 4 other carbon. Each carbon in graphite only forms 3 covalent bond to 3 other carbon. So I mean, there's pretty much as I could say without writing a lot more than the space that has been given for us. Okay. What next? Let me change the color. Explain. So now it's explained in terms of their structure, why graphite is soft but diamond is hard. So it really goes back to this explanation about their structure. So it's in terms of structure. So actually these are bundled from different questions that I jumbled up together. But as you can see, a lot of the questions come back to structure bonding. Okay. Of course, here we are not breaking the structure. We're just talking about the properties that make graphite soft and diamond hard. So what I can do is I can just copy this thing, and then I can just I don't have to write again, but I hope what I explained previously makes sense to you in terms of diamond having a 3-dimensional network of that strong covalent bond, very rigid framework. Therefore it's very hard, very rigid framework, so it's very hard to compress or whatever. But for graphite, you can compress it, and therefore they can slide over each other. That's why it's used as a lubricant, and also it's quite soft because of just overcoming the weak intermolecular forces, which is van der Waals forces between the layered structure. Okay, so that results in the property of diamond being very hard. This results in the property of graphite being very soft. And of course, we use diamond in drilling bits. So at the end of those drilling stuff, you will have a coated diamond. So it's very sharp edges. Well, you want it to be sharp because you're piercing into the ground. You like have that rotating thing that you can pierce into the ground. And if you're coated with this very hard substance that don't break easily, then you can mine into any kind of very hard rock as well without the tip breaking or whatnot. All right. Question 4, the last page of this work. So we have this silicon dioxide structure as well as polyethylene. So you haven't really done polyethylene yet, but this is polymer, and this is actually present in your plastic bag. So a lot of those high density polyethylene, low density polyethylene bag, they're all made of polyethylene, okay, your plastic bags. Silicon dioxide is a component of white sand, so not just any sand, but those white sand. Each silicon is bonded to each silicon, which is the black color one, is bonded to 4 other oxygen. As you can see, 1, 2, 3, 4. All right, and then each oxygen is bonded to 2 other silicon. So the important coordination number there. Each carbon here is bonded to 1, 2 other carbon, but each carbon forms 4 covalent bond. 1, 2, 3, 4. Carbon has 4 outer shell electrons. It uses all its outer shell electrons for forming covalent bond in the structure of polyethylene. And it's a continuous network as this carbon is bonded to carbon, and continues and continue. Polymer is the last topic of your O-level chemistry, and is one of the interesting aspects of the applications of organic chemistry in our daily life. So the melting point of silicon dioxide is, well, thousands, whereas polyethylene starts to melt at 130 degrees Celsius. So this is considered low. This is considered very high. So in terms of structure and bonding, what is the structure and what do you need to break? Why the melting point are very different for 4 marks, okay? So this is comparison. So make sure you're not just stating, you make one statement. It's called a qualifying statement, or statement of intent in the context of whatever is being asked, to compare the strength or the energy required to break whatever is needed here to be broken, and also whatever is needed to be broken in order to melt these 2 substances. Alright, so let's get started. Silicon dioxide, the formula is SiO2. So SiO2 has a giant covalent structure or giant molecular structure. Stick with one and be happy with it. But you should know that question can give you giant covalent structure, which has the same meaning as giant molecular structure. A lot of textbooks, even the syllabus, has started to adopt giant covalent structure for many years. I don't know, giant molecular structure just sticks with me, but you can use giant covalent structure and you will not be marked incorrectly because it's a correct chemistry, okay? So I need to talk about melting it, okay? So melting SiO2, melting it requires breaking a large number, breaking many strong covalent bonds between silicon and oxygen atoms. Therefore needs a large amount of energy. A very large amount of energy, okay? Number 2, so polyethylene. The fact that it has a low melting point, this is considered quite low. Anything below 200, 300 is considered quite low still, alright? So polyethylene has a simple molecular structure. It must have a simple structure, otherwise it will not have such low melting point, okay? Not that you need to know a lot about polymer at this stage, but it's something that you can infer based on the properties such as the melting point given to you. So melting polyethylene requires only breaking weak intermolecular forces of attraction between the polymer, between the molecules, because simple molecule exists as discrete single molecule, right? And then this is my final qualifying statement, okay? I'm comparing why one has such high melting point and the other one has very low melting point. Overall, much more energy is required to break many strong covalent bond than to break weak intermolecular forces. This last qualifying statement is always important because sometimes it's not really comparing breaking strong covalent bond versus this. Sometimes it's about comparing giant molecular structure versus giant molecular structure. So you're actually comparing the strength of the covalent bond that you're breaking. Sometimes it's about simple molecule versus simple molecule. So you're comparing the strength or the energy required to break one van der Waals, well, one intermolecular force versus the other intermolecular force, and therefore you need to think about the factor. Okay, so a lot of comparison come down to what kind of qualifying statement can you make by thinking about the problem given in the context of the questions. What is your stand on this? All right, what can you deduce from it? Okay, this is the last question, which is a dot and cross. So carbon monoxide, as you know, carbon monoxide is a poisonous gas. All right, so this is a poisonous gas. If you breathe in carbon monoxide, it's a silent killer. Okay, so it has a toxic effect on your red blood cell. So once you do more biology, you will learn about red blood cells, and red blood cells carry oxygen. So carbon monoxide compete with oxygen for your occupancy inside the red blood cells, and therefore it prevents oxygen being taken up by your red blood cells. If you can't bring oxygen to your brain, then brain dead, and eventually you pass away. Okay, so draw the electronic structure of carbon monoxide. Electronic structure means dot and cross. That is another name for it. Show only the valence electrons, the outer electrons. To draw this kind of thing, I always like to draw display formula first. CO2 is this, but this is CO, carbon monoxide, so be careful. CO will be like this, but then I would have a lone pair there, because this lone pair is like this. Then oxygen there uses 2 out of 6 outer shell electrons for bonding. So oxygen there actually has 2 lone pair. So oxygen there actually has 2 lone pair. And we have a problem because this carbon here has only got 2, 4, 6. Whereas this oxygen has got 2, 4, 6, 8. So this carbon is not happy at all in order to get 8 electrons in the outer shell of the carbon. So what it does is these 2 electrons can form a covalent bond. So what I do is I will have a very special one where the 2 electrons come from the oxygen, and therefore I'll use a dot for the carbon. So this is a special covalent bond because it's the only way that the carbon can get 8 outer shell electrons, because the carbon has 1, 2, 3 and 4 only, but to get up to 8 the oxygen has 2 lone pair, so the oxygen can use and donate 2 of the non-bonding electrons to form 1 covalent bond to this carbon. Okay, so a lot of students don't know about this structure. It's actually a triple bond. Okay, it's actually a triple bond, and guess what? They do actually tell you triple covalent bond. So when you draw this, you need to be in the context of this. This is not dot and cross, so now for 2 marks you should really be spending lesser than 2 minutes on it. If you know what you're looking for, it will be nice and easy. If you don't know, this will be a struggle and can take you like forever. Okay, so be careful. This is not a normal 3 covalent bonds. This is 2 normal covalent bond and 1 unusual covalent bond. This is your unusual covalent bond. It is still sharing of electrons, but both the electrons being shared in this single covalent bond comes from the oxygen. So if I use dot for carbon, so dot for carbon, I will have cross cross oxygen, but I will have cross cross there, and I'll have dot dot cross cross. So instead of having 2 lone pairs, that means 4 bonding electrons, 4 non-bonding electrons on oxygen, I use 1 of the lone pair, meaning 2 of the non-bonding electrons, to form covalent bond to the carbon, because now the carbon 1, 2, 3, 4, its original electrons, valence electrons, 5, 6, 7, 8. Now this oxygen also has 6, 7, 8. This is nice and happy. This is like this. Okay, so carbon monoxide is one of those things that is quite hard to draw. It's not in your syllabus, but you can read the syllabus and it says you should be able to draw dot and cross for associated or related or something similar given information, given that you want to get to noble gas configuration, what would you be able to do? This is an all-level question, by the way. Okay, so that's it for this tutorial video, and you can ask me anything you're unsure about, and always do correction for your previous work as well. Okay, so if you are watching this and not from my school, not my own students, so don't forget to subscribe to the channel and check out my other created topical playlists that will be suitable for any 14 to 16 years old learners at whatever stage of their curriculum. So thank you for watching, and I'll see you in the next video.